Okay, in this question, we do have an applied force acting on an object going up an incline, and it's our job to find the velocity after going up 1.6 meters along the incline. Okay, well, we'll start off by putting the origin at the very bottom again. We'll assume that this object did start at the bottom and is now going up the incline. A couple things we need to figure out before we do the question. We'll need to know the height after going up 1.6 meters. Now the 1.6 meters is along the incline. We're trying to find the height of it here. So the height is then going to equal 1.6 sine of 21. Because we have a triangle. Okay, here's our angle. Our hypotenuse is 1.6. We're trying to find the opposite side. Then the height is 0.57 meters. And as always, the other thing we're trying to find is the force normal. That way we shorten our conservation of energy equation a little bit. Force normal on an incline is equal to mg cosine theta. So now I'll take 4.5 times 9.8 times the cosine of 21. And our force normal is 41.2 newtons. Okay, now we're ready to go to the conservation of energy equation, and we'll ask ourselves our regular questions we always do. Is the object moving initially? I look at the question, it doesn't specifically state anything, so we will assume that it starts from rest. Is the object initially above the origin? Well, it's starting at the origin, so we'll assume that there's no gravitational potential energy. And one more time, is there any springs attached? No, I don't see any springs in the equation or the question at all, so we assume that there's zero electric or elastic potential energy. And work done. I'm looking for an applied force acting through a distance. I see an applied force of 61 newtons acting through a distance of 1.6 meters. So therefore, we do have work being done in the question. And that's all we have, so I'll give it 4 boxes. On the final case, we're at the top of the incline, and it's our job to find the velocity at the top of the incline. So I'm going to assume that it is moving at the top. I'll give it at least 1 box of kinetic energy. Since we're sliding up, I don't think it'll be that fast. And then we ask, are we above the origin when we get there? Now the origin, again, is the horizontal surface. So yes, this object is above the origin. So there would be gravitational potential energy. We give it 2 boxes of gravitational potential energy. Any springs attached in the end? No, I still don't see any springs attached. So no elastic potential energy. And any thermal energy? Well, I'm looking for a sliding coefficient of friction here, and I see a 0.33. And again, the object is sliding. So unless it states it's a frictionless surface, and I will assume there's thermal energy. And in particular, since there is a coefficient of friction, we can assume that there is a thermal energy. So the conservation of energy equation becomes work equals kinetic energy plus gravitational potential energy plus thermal energy. Okay, now our job is to complete this equation by plugging things into it. I know work is force times distance cosine of theta. So my applied force is 61 multiplied by my distance gone, which is 1.6. And lastly, cosine of 0. Now this one causes a little confusion because the 21 degrees here is often placed in this cosine theta here. But I need to remind you that the applied force is parallel to the motion, and the 21 degrees belongs to the incline. So remember, when we're looking for the cosine of the angle, we're looking for the angle that the applied force is acting at relative to the direction of the object. So again, the 21 degrees belongs to the inclined plane and does not belong to the applied force. Equals kinetic energy, I'll go 1/2 the mass, which is 4.5, and multiplied by velocity squared. Now again, we don't know velocity. And anytime we don't know velocity, we're using the kinetic energy portion of our conservation energy equation to solve for velocity. Then we go plus gravitational potential, so that's 4.5 times 9.8 times the height previously found at 0.57. Okay, and now we need to add the thermal energy, which is force normal multiplied by our mu multiplied by our distance. I'll write it just a little lower to make sure I fit it in. So 41.2 is our normal force multiplied by 0.33, which is our coefficient of friction, and finally multiplied by our distance. Now this is our sliding distance of 1.6. So again, notice our sliding distance is used for our friction, and the height, 0.57, is used for our gravitational potential energy. And again, being careful, solving for velocity using careful algebra techniques. Velocity then is 4.7 meters per second when it gets to the top of the incline. And that's how you do applied forces, okay, with inclined planes.